Hello friends, welcome back to my YouTube channel. Today in this video we will discuss past paper solution from ideal gas from October-November series 2010 to 2018. Before moving to questions, I recommend you to see my first video on ideal gas. In that video we discuss what is ideal gas, what are the different postulates, and we develop some formula, some theory about ideal gas. Now let us move to our first question. In this question, it is asked that state the basic assumption of kinetic theory of gas that leads to the conclusion that the potential energy between the atoms of an ideal gas is zero. This is from October-November 10, paper 4.2. In this question, it is asking that in ideal gas, potential energy is zero. And what is the postulate that leads to this conclusion? And if we see our postulates in our first video, there is clearly written that there is no intermolecular attraction or repulsion between the atoms of an ideal gas. If there is no intermolecular attraction or repulsion between the atoms, then there is no potential energy. The minimum fundamental criteria required for potential energy is there should be some force of attraction or repulsion. If there is no force of attraction or repulsion between the molecule, then potential energy will be zero. Now let us move to this question. State what is meant by the internal energy of a substance. Sum of kinetic and potential energy of atoms in a system due to random motion is known as internal energy of the substance. So here internal energy means kinetic and potential energy, sum of kinetic and potential energy of the system. So let us move to this question. Explain why an increase in internal energy of an ideal gas is directly related to the rise in temperature of the ideal gas. Here it is clearly saying that increase in internal energy of ideal gas. There is ideal gas. In ideal gas, internal energy means kinetic energy plus potential energy. In ideal gas, potential energy is zero. In ideal gas, potential energy is zero. It means internal energy is equal to kinetic energy in ideal gas. Internal energy is equal to kinetic energy in ideal gas. So is directly proportional to rise in temperature. We already know that kinetic energy is directly proportional to temperature. If we increase temperature, then average kinetic energy of the gas molecule increases. Here internal energy of ideal gas means kinetic energy because potential energy is zero. If kinetic energy is increasing, then temperature will increase. Because of that, increase in internal energy is increase in kinetic energy. Since potential energy is zero, sum of average kinetic energy is temperature, so temperature rises if internal energy is increased in ideal gas. Now let us see, state the basic assumption of kinetic theory of gas. This was asked for 4 marks. So if you write 4 assumptions, and that will be okay. In ideal gas or in kinetic theory of gas, there is no force of between there is no attractive or repulsive force between the molecule. Volume of molecule is negligible as compared to the volume of the gas or volume of container. Random motion in all possible direction. Gas molecule can move in random motion in all possible direction. There is elastic collision with the molecule and wall of the container. They always collide elastically. Duration of the collision is very small. A molecule and molecule collision is very common. One molecule can find trillions number of neighboring molecule, and then when they collide with the wall, between the wall and the molecule, and there will be large number of collision between the molecule before they collide to the wall. So these are the some assumptions. Now let us see this. Use the equation of pressure of an ideal gas to deduce the average translation kinetic energy of molecule of ideal gas is this. So we have to use equation of pressure, means P is equal to 1/3 rho c square, where R is molar gas constant, Na is Avogadro number, Avogadro constant, T is the thermodynamic temperature of the gas. Now let us see this. We know that P is equal to, pressure is equal to 1/3 rho c square. This rho is density of the gas. Density is mass by volume. Now if I take this volume to this side, PV is equal to 1/3 nmc square. This m is the total mass of the container. If one container is there, this container contains large number of n molecules, capital N molecules. If mass of one molecule is m, then total mass will be small m into n. This m is the mass of molecule, n is the number of molecule. In the case of identical molecule, we can write this. So I can replace this capital M by small m into n over here. and then we know that PV is equal to nRT. This is called ideal gas equation. Here is also PV, here is also PV, so I can write 1 by 3 mn c square is equal to nRT here. According to question, we need to find kinetic energy. Kinetic energy is half mv square, or here half mc square. Here I have m, here c, so I collect mc square here, and 3, I'll take 3 to that side, and the small capital N will be here. Then RT, this small n by capital N, this small n by capital N will give us 1 by NA, 1 by NA. This small n by capital N is 1 by NA, because if Avogadro number is Na for one molecule, for one molecule for 1 mole number of molecule is this. If there are n moles, then number of molecule will be this amount. N is number of molecule. So 1 mole contains Avogadro number, 2 mole contains 2 into Avogadro number, 3 mole contains 3 into Avogadro number. In such way, total number of molecule in a container is n times Na, and from this n by Na will give us 1 by Na, and this R is a universal gas constant, Na is also constant, and according to our that expression, half mc square is equal to Ek, and we need to prove this expression. Ek, or mean of kinetic energy, or mean kinetic energy, is equal to 3 by 2 R by Na times T. That is here. By doing this, we will get our answer. This is the answer. Now let us see this. Write 2 assumptions of kinetic theory of gas. We already know here 5 assumptions. Among these, you can write any 2 assumptions here. Then using the kinetic theory of gas, it can be shown that the product of pressure and volume of ideal gas is this. This is the statement, this is the question. Now we need to write the meaning of this. N is here, N is number of molecules, capital N is number of molecules. C square is mean square velocity. If you see this, this symbol is mean, this is square, and this is velocity, so we can call this mean square velocity. At first, mean, this symbol is mean, and then there is square, and then velocity, so mean square velocity. Here use the expression to deduce the mean kinetic energy of the gas is equal to this. We already solved this, we know this, and then we already solved this in previous question, and in that question we did till this second last step. Our Ek was 3 by 2 R by Na times T, but in this question we need to find 3 by 2 Kt. R is constant, Na is also constant, Avogadro constant. If we divide these 2 constant, we will get new constant. That new constant is K. So 3 by 2 Kt will come here. This K is called Boltzmann's constant. This K is called Boltzmann's constant. Boltzmann's constant will come here, and its value is 1.38 into 10 to the power minus 23, and unit will be, we can find unit from here. If we take T here, if we keep K over here, and if we take T to this side, then Ek is in joule per Kelvin. Joule per Kelvin is unit of K. So K is Boltzmann's constant. Now let us see this. State what is meant by internal energy of substance. We already solved this. Kinetic and potential energy of atoms in a molecule due to the random motion. Use the equation B second to explain that an ideal gas or change of internal energy is this. See, in the case of ideal gas, we need to show internal energy is directly proportional to temperature, or change in internal energy is directly proportional to change in temperature. In ideal gas, there is no intermolecular force, so potential energy is 0. If potential energy is 0, internal energy is directly proportional to kinetic energy, and kinetic energy is directly proportional to absolute temperature. Because of that, internal energy is directly proportional to absolute temperature. Because of that, internal energy is directly proportional to absolute temperature. So change in internal energy is directly proportional to change in absolute temperature. Change in absolute temperature. This is very interesting question. A student suggests that when an ideal gas is heated from 100 to 200 degrees centigrade, the internal energy of gas is doubled. He is saying that here temperature is doubled, internal energy of gas should be doubled, but in the case of ideal gas, IDEAL should be here. State what is meant by the internal energy. We already solved this. By the reference of one of the assumption of kinetic energy of the gas, deduce what is meant by internal energy of gas. We already know this. Now let us see this. A student is saying that internal energy of gas is doubled, and here is question. State and explain whether the student's suggestion is correct or not. If we see this, if temperature is double, then kinetic energy will be double. If kinetic energy will be double, then internal energy will be double, because potential energy is 0 in the case of ideal gas. This is valid only in the ideal gas. In ideal gas, internal energy means kinetic plus potential energy. If potential energy is 0, then kinetic energy increases with internal energy, or internal energy increases with kinetic energy. Here temperature is increased. Temperature is increased means kinetic energy is increased, because average kinetic energy is temperature, sum of average kinetic energy. Now if the temperature is doubled, kinetic energy should be doubled. If kinetic energy is doubled, then internal energy should be doubled. But this temperature is in degrees Celsius. This temperature is not in Kelvin. If temperature in Kelvin doubles, then this happens. But here 100 degrees centigrade means it's 100 plus 273, that is 373 Kelvin. And 200 degrees centigrade means 200 plus 273, that is 473 Kelvin. If we see this is not doubled. If reading in Kelvin scale is double, then this could happen, but temperature in degrees Celsius is double means temperature is Kelvin scale is not doubled. So answer will be like this. We know that kinetic energy is directly proportional to absolute temperature. Here temperature is doubled in degrees Celsius, not in Kelvin scale. So internal energy is not doubled. Student suggestion is not correct. See this. A gas cylinder has this volume. Volume is in centimeter cube. If it is in centimeter cube, we need to multiply 10 to the power minus 6. 10 to the power minus 6 will make this meter cube. A helium of 4 gas, 4. Helium 4 means its mass is 4. Its mass is 4 means 4 AMU. 4 AMU means 4 into 1.67 or 1.66 into 10 to the power minus 27 kg. This will give us kg. 4 AMU means 4 into 1.67 into 10 to the power minus 27. That will give us mass in kg. And pressure is here. Pressure is here and temperature is also here. Now determine for the helium gas the amount of mole. Amount of moles means you need to determine N. N is called amount in mole or amount of substance. We have given P. We have given V. P into V is equal to nRT. Our R is 8.31 and T here is temperature. We need to convert this temperature into Kelvin, and the Kelvin corresponding Kelvin temperature will be 12 plus 273. This will give us 200. Here it should be 200 3 to 585. It's not 85, 285, and this will give us amount of substance, that will be 5.4 mole. 5.4 mole. Now next the number of atoms. We already know that number of atoms means number of mole times Avogadro number. Number of mole times Avogadro number. We know Avogadro number, this is a constant, and number of mole is 5.4 from this calculation, 5.4. Now by using this we will find the number of atoms. We got number of atom, this 3.26 into 10 to the power 24. Calculate RMS speed of helium atom. We know that PV is equal to 1 by 3 nmc square. We know P, we know V, 1 by 3 is already given. N is this is N is equal to 3.26. Number of molecule is this, and then mass is I'm sorry to write this N here. This N cannot be that N should be capital N, and capital N is this. Sorry for writing small n. And M, mass is, we already discussed, mass means 4 AMU. 4 AMU means 4 into 1.66 into 10 to the power minus 27, that will be kg. And on solving this we will get c square. C square is not our answer, because RMS is saying, in the case of, if you know c square, we can calculate CRMS by taking the square root. Square root of this will be this, and unit will be meter per second. Now let us move to this question. A cylinder contains 1 mole of ideal gas. The volume of cylinder is constant. Calculate the energy required to raise the temperature by 1 Kelvin. 1 Kelvin is already given here, and we know that energy is equal to 3 by 2 nkt, and nk can be written as R here. Nk can be written as R here. Do analyze the formula, and 1 mole is written here. N is 1 mole. So we can write this. And our K is 8.31, and change in temperature is 1 Kelvin. By solving this we will get 12.5 joule. 12.5 joule is the answer for this question. Now let us see this. The volume of cylinder is now allowed to increase so that gas remains at constant pressure when it is heated. Explain whether energy required to raise in temperature of the gas, why 1 Kelvin is now different. See, in this case volume is increasing. In this case, sorry, let me see, where was it, yeah, this is here. In this case, cylinder, the volume of cylinder is constant. You need to take care of these things. Volume of cylinder was constant, because of that our answer is this. Now the same case is here, but volume is not constant. Volume of cylinder is now increasing. Now question is asking again, we need to raise the temperature by 1 Kelvin. In this cylinder volume was constant, so in order to raise the temperature by 1 Kelvin we need to supply this energy. But in this case volume is not constant. Question is clearly saying that volume is increasing, this is increasing, side are increasing, they are moving, and we need to again increase the temperature by 1 Kelvin. Now how much energy is needed? Greater energy is needed, because this volume is increasing means this have to push, this have to take away some molecule of atmosphere far from it. Because of that its volume increases. So on taking molecule far from its this side, the increased portion of the cylinder, it has to do some work. Because of that extra energy is needed. So greater energy is needed in the case of volume increases, because cylinder has to do some work against atmosphere. Now let us see this. In this first question, these two questions are repeated. If you see this, a storage cylinder of an ideal gas has volume is this in meter cube. You do not need to convert this. Temperature is this, pressure is this. Now we need to show that amount of gas in the cylinder is 6.1 mole. So we know that PV is equal to nRT. Now we need to find the value of N. P is given, V is given, R is constant, which is, we know the value, and it is also given in data booklet. And temperature is 23. We need to convert that into Kelvin or absolute scale. So we'll get 6.1 mole answer. Now in this case, the gas is leaked slowly from the cylinder, so that after 35 days the pressure has reduced to 0.40%. In this case now pressure is reduced. Pressure is reduced by 0.40% because of leakage of the molecule from the cylinder. The temperature remains constant. Temperature is constant. We can take this temperature here, 23. Temperature is constant. Calculate the average rate in atoms per second at which gas escape from the cylinder. Here gas is leaked, because of that pressure is decreased, means pressure is indicating the amount of substance. This much amount of 0.40% of pressure is decreased because of leakage of gas, means pressure is directly proportional to amount of substance. So loss of substance in mole is 0.4. We need to convert this into fraction, percentage 0.40 divided by 100, and our mole was 6.1 mole. It means 0.244 mole of substance is already out of the cylinder because of the leakage. This means how many molecules are escaped? We know that there are this amount of molecule in 1 mole. This is Avogadro constant. So this molecule moved away. This molecule has been moved away from the cylinder in 35 days. Now we need to find the per second, means this amount of molecule divided by 35 days. That will give us amount of leakage of molecule per second. So we will solve this amount. This amount of molecule has been leakaged in 35 days. This is 35 days. 35 into 24 into 60 into 60. This is in now second. Now we can get this answer. This is the answer for this question. This amount of molecule has been, in this rate molecule has been went out from the cylinder. A fixed amount of gas has initial volume. This is initial volume. This is initial pressure. This is initial temperature. And this state has been changed to this. This is final volume, final pressure, and final temperature. Now we need to show these two states are the gas in which it behaves ideal case. This is the ideal case. Question is saying that we need to prove that this is the ideal gas equation or ideal case. We know that ideal gas equation is PV is equal to nRT. Here gas is fixed, because question is clearly saying that the amount of gas is fixed. It's just pressure and volume are changing, but amount of substance remains same. As amount of substance remains same, N remains same, R is also constant. So we need to show that if PV is equal to nRT, if gas satisfies this, then that is ideal gas equation. If these two things are constant, then ratio of PV by T is also constant. That is, if we show PV by T in this case is equal to PV by T in this case, then both are ideal gas, because N and N are constant. N and R are constant. So from this case, if we calculate P1, B1, T1, we will get this. In this case, if we calculate P2, V2, T2, we will get this. They are same. So they are satisfying, they are following PV is equal to nRT. Whatever be the pressure, whatever be the volume, but they are satisfying PV is equal to nRT. It means both are following ideal gas equation. So this is the proof for the ideal gas equation. Now let us see this. The total energy supplied to the gas for this change is 569 joule. Determine the external work done. Work done means pressure into change in volume. Pressure into change in volume. If you see this pressure are same here, pressure are same here in both case, pressure are same, volume is just change. This is V2, this is V1. So V2 minus V1 will give change in volume. That will give us 228 joule. This is the work done. This is the work done. Pressure into change in volume. Our formula to calculate work done by the gas is pressure into change in volume. Now let us see this. The mean square speed of atom of a fixed mass of ideal gas at 32 degrees centigrade is this. The gas is heated at constant volume at a temperature this. The rise in Kelvin of the temperature of the gas. So this is the final temperature, this is initial temperature. So change in temperature is this 48 degrees centigrade, and we know that rise in temperature in centigrade scale is same as that of rise in temperature in Kelvin scale. So this will give 48 Kelvin. In another way, you can convert this 80 into Kelvin, and you can convert this 32 into Kelvin, and if you calculate the difference will be same. This is rise in temperature in Kelvin. As its degree centigrade changes from 32 to 80, rise in temperature in Kelvin will be 48. Now let us see this. The number of molecules per volume in a gas is n. It is assumed that all molecules are moving with velocity v. The pressure exerted by the gas on the wall is 1/3 nmve square. This n means here number of molecule, because it is clearly saying that this is number of molecule. This is not number of mole here in this case. In this case, this is not a number of mole, number of molecule. Explain the reason why we modify this. This is v square. Why we are writing v square? In a gas container, the molecule can have different velocities, so we need to take the average velocity. Gas molecule are moving in the different range of velocity. Some have less velocity, some have more velocity. Because of that, we need to take care of the average velocity. We need to calculate average velocity. Here average of v square is c square. Because of that, we need to modify the formula. Now let us see this. The density of ideal gas is this, at a pressure this, and temperature is this. Calculate root mean square speed. Our formula is P is equal to 1/3 rho c square. Pressure is this, and this is our density, and we need to convert this temperature is not needed, sorry, here. So pressure, we know that 1/3 rho c square, and we get c square, and our answer is root mean square. Question is saying RMS. RMS means we need to take square root of this value. Square root of that value will give us 500 meter per second. So this is the answer, 500 meter per second. Now let us see this. Calculate mean square speed of molecule at 277 degrees centigrade. Here our speed at 27 is 500 meter per second. At 27 is 500 meter per second. Now question is asking to find the RMS speed at 207 degrees centigrade. 207 degree. So now let us see this. Calculate the mean square. It's not saying root mean square, it's saying mean square velocity. So now let us develop this. You don't need to write this in your examination. We know that half mc square is equal to 3/2 r by n a into t. We already proved this. If you see our before slide, you will get this. If you see some slide before, then you will see this. So if you see this, these are constant, these all are constant. So c square is mean square velocity, that is directly proportional to t. Here also we want to find the mean square speed. If I write this, then c square, c1 square will be constant time t1, and c2 square 2 will be constant time t2. This is the first case, 1 1, and this is the second case, 2 2. If you divide this, we will get c1 square 1 is equal to c2 square 2 is equal to t1 by t2. This is the mean square velocity at the given temperature t1. This is mean square velocity at the given temperature t2. Here are two cases, temperature 1 velocity 1, temperature 2 velocity 2, and our temperature 1 is this and velocity 1 is this. Temperature 1 is this, velocity 1 is this. On solving that, we will get our answer. On solving that, we will get our answer, and on solving this, we will get our answer. So C1 square is if we are dealing with root mean square velocity, then in that case formula will be this. If I take square root of this value, if I take square root of this, then this will be RMS value of 1, this will be RMS value of 2, and this will be root under T1 by root under T2. Temperature should be in Kelvin. Here C1 square, if I am calculating mean square velocity only, this should be mean square velocity, not root mean square velocity. Mean square velocity is here 2.5 into 10 to the power 5. So I need to write here 2.5 into 10 to the power 5. This is mean square. We are not dealing with root mean square here. So mean square velocity, I need to keep this, and I need to use this formula. By using this formula, I will get my answer. You need to take care of this thing while solving this question. See this. The equation of the state of an ideal gas of volume V at a pressure P is PV is equal to nRT. What is meant by the symbol N? Here N means number of moles. This is not a number of molecule, number of moles, and T means absolute temperature. If you write temperature only, then that will be wrong. Absolute temperature or Kelvin temperature, temperature in Kelvin. Okay, an ideal gas is held in a container of volume this at a pressure this. The temperature is 100 degrees centigrade, so that number of molecule of the gas in the container is this. So we know this is our what is the volume, this is our pressure, this is our temperature, this volume is in meter cube. Now by solving this PV is equal to nRT, we will get number of mole will be 0.38. If we know number of mole, then number of mole into Avogadro number will give number of molecules. Number of mole into Avogadro number will give number of molecules. That will be, after multiplying this 0.38 with this Avogadro constant, we will get this. This is the answer for the question B. Now let us see this. Using the data in above B to estimate the mean distance between the molecule of gases. We know that total volume is this. We know that total volume of gas is given here. This is our total volume here. This is total volume, and number of molecule is also, we know the number of molecule, there are this number of molecule. So volume of one molecule will be this divided by this. This is the volume of one molecule. If we know volume of one molecule, then our formula is volume of molecule is equal to 4 by 3 pi r cube. Then this r is our answer, because we need to calculate mean distance between the molecule are, if they are located like this, then this will give us mean distance. So we will calculate mean distance by using this formula, or we can directly calculate the 1/3 root of this, and that will also give us the mean distance for the molecule. Now let us see another. Here this is the first case, this is the second case. We need to find T. If the gas is ideal gas, then our formula will be P1 B1 T1. P1 B1 T1 is equal to P2 B2 T2, and we will get our T2, because P1 is given here, P1 is given here, B1 is given here, T1 is given here, P2 B2 are given, T2 is not given. So that will be our answer. Now let us see the second part of this question. In this question, it is asked that a change in energy of the gas is 240 joule will result in an increase of pressure to the final value this at a constant volume. The thermodynamic temperature becomes, this is the information here. Now we need to find amount of substance. After finding temperature, we need to find amount of substance. For amount of substance, we can use formula PV is equal to nRT. In both cases, we know T here also we can use PV is equal to nRT, and we can find N. Here also we can use PV is equal to nRT, and we can find small n. So that will be our answer, and answer will be 0.016 mole. This is the answer for that question. Thank you very much. These are all the questions from October-November series, and question were not asked in 2017 from this chapter, and some questions were repeated. Because of that, we have completed the questions from ideal gas. Here almost all questions are repeated, but some questions are different. So try to practice the different questions, try to find the logic, hidden logic, the trap of Cambridge question, and then you can solve the question. Understand questions carefully and then start to solve. Thank you very much.